Hey everyone, so I'm not sure if you had the chance to see my correction, but the differential or the derivative of a to the power of x is definitely not e to the power of x times ln of a, and it's actually, in actual fact, it's going to be, you know what, I'm just gonna let you see. I'm gonna figure this out, and then you'll get the chance to actually understand what it is. So let's suppose we have a y, and that y is equal to a to the power of x, and we want to differentiate it. So we can use logarithmic differentiation, which is basically just another way of putting log rules together with exponential rules and implicit differentiation on top of everything. So what we're going to do here is we're going to, first of all, we have this exponent here, which is not actually an exponent, it's x. So it's not a numerical exponent. We can't apply the power rule here. So we have to use a natural logarithm, preferably, in order to put the x as a coefficient rather than an exponent. So then we have ln of y equals x ln of a. It's just a basic logarithm rule. And just in case you don't know them, if you have logarithm plus another logarithm, that's the same thing as the logarithm of the product of them. And the same thing applies to negation, to subtraction. And you have more rules. I'm going to discuss them in a different series playlist. So I'm just going to focus on that. So the next thing you might want to do is you might want to find the derivative of both sides. So here we applied the natural logarithm, and here we want to apply the derivative. So then here we would have 1 over y, just like you have the natural logarithm of the derivative of the natural logarithm, which in the last video we showed it's 1 over x. If the input is y, we do exactly the same thing, but we replace x with y, and we apply the chain rule, because y is a composite function of x. So then we have this. And that is, what is this? Well, ln of a might be a natural logarithm, but it's still a constant. There's no x here, so there's no variable, so it's a constant. So just like we have any line or any linear function with the formula a times x plus b, and we don't have a b here, b equals 0, it differentiates to a, because when you raise x to the power of 1 minus 1, which equals to 0, it's the same thing as just doing 1 times that constant. So then what we get when we differentiate is we get ln of a. And now we just want to rearrange, just like we do in any other algebra problem. So we want to find dy over dx. So that means we are dividing ln of a by 1 over y, which means we're multiplying the natural logarithm of a by y. And what is y equal to? Y is the same thing as what we said here, a to the power of x. That's the problem we started with. So if we kind of want to be more neat about this, we can say that the derivative here, dy over dx, is equal to a to the power of x times ln a. And that is not the same thing. That is not the same thing as e to the power of x times ln of a. That's a mistake. I was probably tired when I uploaded that video, but this is the actual value here. And we just proved it, and yeah. Hopefully I'll get to make some videos on functional analysis now. See you in the next video.